Greetings everybody, and today we're going to be taking a look at vector space homomorphisms. So far what have we done? We have defined these vector spaces V, which is what we started with the set, and then we add on these additional structures plus and scalar multiplication. And this forms a vector space if these two operations satisfy those certain 10 axioms. And it's now with homomorphisms, what is our goal? We want to consider another such vector space, let's say W plus and scalar multiplication, and we want to study maps that go between these two vector spaces. And there are particular types of maps we want to take a look at, namely homomorphisms over here. So first of all, what are homomorphisms? Well, homomorphisms are simply the structure preserving maps between the two spaces. So if you've studied a group theory before, you know there are those group homomorphisms which preserve the group structure. If you've studied topological spaces before, you know there are homeomorphisms which preserve certain topological properties and so on. With the vector space homomorphisms, what is the structure we're preserving? Well, we're preserving the linear structures, so we're going to be taking a look at linear maps next. So let's consider a map between V and W. We'll call it phi over here. So phi goes from V into W. And now we call phi linear if it satisfies these following properties. First of all, if you take phi and you act on the sum of two elements in V, so let's call it V1 plus V2 over here, then this is going to give you phi of V1 and then plus phi of V2. And it's also worth mentioning that these pluses that I've written down over here, they're actually different pluses. So because this plus over here acts on two elements of the vector space V, whereas this plus over here, it acts on two elements of the vector space W, because phi V1 and phi V2, well, those are both elements of W. So this is actually the plus on W over here, this is the plus on V. So if I want to, I can put a little V subscript and W subscript, and also on the scalar multiplication to remind us that these operations over here, they're completely different. So the second condition is that if you have phi of let's say lambda times V over here, this is equal to the lambda times the phi of V. So notice this scalar multiplication over here is from the vector space V. This scalar multiplication is from the vector space W, because again, phi V is an element of W. Another important thing to mention is that these two vector spaces must be over the same field F. And this is particularly important over here in order for this second condition to make sense, because notice if these two were over different fields, let's say V was over the field F1 and W was over F2, then well, first of all, this lambda would come from the field F1. If we require this linear property over here, this lambda jumps out to the front. Now we have a scalar multiplication with W. But if phi V is an element of W, that means you can only scalar multiply by elements in the field F2, because let's say F2 was the field of W. But that's a bit of a problem because we already know lambda is from the field F1, and that becomes a problem because you can't multiply different elements over different fields without adding even further structure, which we don't want to do. So it does make sense that these two vector spaces must be over the same field so that we don't have any problems with the scalar multiplication. So as a picture, we can actually do a little nice diagram for this. Let's say this is the vector space V over here, and we have another vector space in W, and let's pick two elements in V, let's say V1 and V2 over here, and let's say we add these two together with this map plus on V. This is going to produce for us, well, V1 plus V2. Okay, so this is what happens in V over here, and let's say we map everything over to W. So we have a phi over here, phi, and we'll save that for later. But what happens to phi of V1? Well, that's just phi of V1. Let's say that's some point over here, and then say we have another point over here, which is phi of V2. So if we add it in V, well, we get this new element V1 plus V2. Let's say we add these two in W now, so we grab these two elements, we add them together on W, and then we get the element of phi of V1 plus phi of V2. And this is actually where the structure preserving comes in. If you notice over here, we defined phi V1 plus V2, which is this guy over here. If we map it over, we require it to be the same as phi v1 plus phi v2. And this is nice because notice it doesn't matter if you add these two elements in v and then send them over to w, or if you send them over first and then add in w, it doesn't matter because you still get the same result. So in fact, this map phi over here preserves that addition structure, and you can draw up a similar diagram for scalar multiplication as well. Okay, so those are linear maps. It preserves the structure. So the next part of this video, we're going to be defining this new set, which we call hom over here. And hom takes two arguments, let's say v and w. And how is this hom set defined? Well, it's simply defined to be the set of all these maps over here, which go from v into w. And we have the extra requirement that phi is linear. So this is the set hom v-w. So between these two spaces v and w, you think of all the possible linear maps that there could be, you throw them all into one set, and you call that set hom v-w. So hom v-w, that's the set of all these linear maps. It might seem a bit weird because, well, what exactly is a set of maps over here? That's a bit funny. But remember, a set, well, that's just simply a collection of, well, any elements you really want to. And the elements we're considering in this case are just a bunch of linear maps. So any single linear map between these two spaces v and w you can think of, throw them into the set. That's called hom v-w. And my claim is you can actually turn hom v-w into a vector space. So that's what we always do when we define vector spaces. We always start off with a set, and then we add on these additional structures over here, or these additional maps, which satisfies a bunch of axioms, and that turns into a vector space. That's what we're going to do now. We start off with a set over here, a set of all these maps, and we're going to define two operations, the plus over here and scalar multiplication, and if they satisfy certain properties, then we call the set along with those other operations a vector space. So first of all, let's define this addition over here. Now this addition, I put a little circle around just to distinguish it from these two pluses over here, but this is just for notational purposes. You could just write a plus, you don't need the circle plus. So how does this circle plus work? It's going to take two elements of hom v-w in this Cartesian product. So hom v-w cross with hom v-w once again. And what is it going to do? Well, it's going to send it to nothing else than hom v-w. So how does this circle plus work? We're going to take two linear maps, let's call them phi and psi, and we're going to add them together using this circle plus over here. And this is, well, hopefully it's going to produce for us another linear map. Now, so if this is a map, phi plus psi, we can understand this map if we let it act on some elements. Now, what do we let it act on? Well, this is supposed to be a map from v to w, so it only makes sense that we let this act on some kinds of element of v into v. So this actually works for all v in your domain vector space, capital V over here. So for you pick any element in v, you act on with this map phi circle plus psi over here, and you define this to be equal to phi of v, and now we have the plus psi of v. So phi and psi, those are maps from v to w. So phi of v, psi of v, those are actually elements in w. So this is actually the addition of w over here. So this is how we're going to define our circle plus. We take two linear maps, phi and psi, and what happens if we add them together? Well, we get this new map, which we call phi circle plus psi. And this is a map over here. Again, it should be a map from v to w, so we let it act on a v. This is how we define it. Now, so far, all this map does, it takes in an element of v, spits out an element in w, which is what this is. This is an element in w. But if it were to be in a hom v-w, then it must be linear as well. So what we have to do now is we have to check that this phi plus psi is actually linear. We know how it operates. Well, here's the definition right here. We also have to check that this map over here, this phi circle plus psi, is also a linear map. So let's do that. We need to check these two conditions over here. So we're going to check that phi circle plus psi, this new map that we have, is linear. How do we do this? Well, first of all, let's pick two elements in v, we'll just call them v1 and v2, and let's see what happens. So phi is circle plus psi acting on v1 plus v2. Well, first of all, what can we do? The only thing we can really do is use the definition of phi circle plus psi. So by definition, this is equal to, well, we take the phi of whatever's in here, so that we take the phi of v1 plus v2, and then we add it with, so plus on w, the psi of whatever's on the inside over here, which is v1 plus v2 yet again. And now you may notice that for phi and psi, those are both linear maps because they come from HomVW, which means we can use the linearity properties of phi and psi to split this up even further. This is equal to now, well, we have phi of v1 plus on w, phi of v2. And then now, again, we have a plus on w, we have psi of v1 plus w, once again, psi of v2. So it's pretty clear all these pluses are on w, and I'll just get rid of them just to make it look less cluttered. And now what we can do now, we know addition on vector spaces is associative and commutative. We can rearrange all this a little bit. We can rearrange it to phi of v1, and I'm going to bring the psi of v1 into here, so psi of v1, and then I'm going to put this phi of v2 next. And then we're going to have psi of v2. Okay, and what can we do from here? Well, we can kind of reverse this definition over here, because notice if we have two maps acting on the same element, well, we can kind of compress that down into phi plus psi. That's what we're going to do next. So here in these first two terms, we have phi circle plus psi. We can compress them together because they act on the same element v1. Same thing over here, we have plus phi circle plus psi. We can compress them together into 1 because they act on the same element v2. So hence, what did we show over here? We showed that phi plus psi, v1 plus v2, we can actually split this up across this addition over here. We get these two new terms. Now we have to show a similar thing for the second property, 2 over here. We have to check now that if we pick any element lambda in here, we have to check that if we have phi circle plus psi, if we have it act on lambda times the v over here, we can pull the lambda out. So again, what we're going to do, we're going to use the definition of this circle plus over here. So this is, by definition, well, we have psi acting on this lambda v, and then plus psi acting on this lambda v. So remember, if you have two maps added together acting on something, well, you have the first map acting on that something plus the second map acting on that something. Now remember, phi and psi, those are linear maps, and if they're linear, then you can pull this constant out on the outside. So this is, in particular, it's going to be lambda phi of v, and then we have plus lambda yet again psi of v. And notice over here there should be dots over here, these scalar multiplication symbols, which are the scalar multiplication on w, but we can hide it because it's pretty clear. Now the next thing we're going to do, we're going to factor out lambda. So we're going to have lambda of phi of v plus psi of v. And now, just like before, we're going to compress these two maps together into one, like so, because they're acting on the exact same element. So this is, we can rewrite this as lambda times phi circle plus psi, and all of this is acting on v. And as you can see, what we've done is we've managed to show that if we have a lambda in here, we can pull it out to the very outside of this map phi plus psi, like so. So in fact, since this map phi plus psi over here satisfies these two properties, then we call it linear. So indeed, this map phi plus psi over here, it actually lands in a HomVW. It's another linear map between v and w. The next thing we're going to do is we're going to be defining the scalar multiplication. Again, I'm going to put it into a little circle just to distinguish it from these two dots over here. But again, just more notational purposes. So how does this scalar multiplication work? Well, obviously we need an element in the field, and we also need an element in HomVW, which is what we're trying to make into a vector space. So we take two elements over here, and well, again, we're going to map it into, yet again, a HomVW. So let's do this over here. Let's try to define this. So again, for all v in your vector space, what do we want? We're going to consider a scalar, let's call alpha over here, and then we're going to take the scalar multiplication with some phi, let's say. So this is a linear map in HomVW. This is just some scalar in the field f. Now this is supposed to be a new map in HomVW. Well, let's just first of all define it as a map from v to w, and we'll try to prove it's linear later on. So if it's a map from v to w, well, this whole thing over here, this is a map. It's going to eat an element in v, so that's why we have for all v and v. And how are we going to define this? We're going to be defined as 2b. Well, kind of similar to before, we're going to have this alpha. times phi v. That's how we're going to define it. And of course, this times over here, that's the times on W, because phi v, that's clearly an element in W. So notice the field F that we want to construct our hom VW vector space over. This field comes from the same field underlying V and W. Okay, so we have this map over here. So far, we've just some random map, and now we have to show that it's linear in order for it to land back in hom VW. So in order for the scalar multiplication operation to close. So what are we going to do now? We're going to check that alpha circle times phi is linear. How do we do this? Well, very similar to before. Let's check the first condition over here. So let's take this map, alpha circle times phi over here, and what we're going to do is we're going to let it act on the sum of two elements in V. I'm going to call them V1 plus V2, just like before. And again, the only thing we can really do is use the definition of this circle times, which is that we can pull the out for out, and then we do the times on W, and then we have phi of V1 plus V. So this is the argument, it's still the same argument in here. What we've done is kind of just pulled the alpha out. Okay, next thing we can do, we can use the fact that phi is a linear map, because obviously we can see that it comes from hom VW. If phi is linear, then let's use this first linearity property to split it up a little bit. This is going to be alpha. Let's use some brackets over here. So we have phi of V1 plus phi of V2. Again, this plus is the plus on W. And remember the distributive laws for vector spaces. These are going to be elements of W over here, this phi V1 and phi V2. So let's distribute. We're going to get alpha times phi V1. And then we're going to have a plus alpha times phi of V2. And now what we're going to do, kind of similar to before, we're going to recompress this alpha and this phi into one singular map. So over here, we're going to get alpha. Now, if we compress these two together, this is not going to be any ordinary times, it's going to be the times on the hom VW, because this is a linear map. So circle times phi, this whole thing is going to act on this V1. Okay, and then very similar for here, we're going to have a plus, we're going to have alpha times this phi, and this whole thing acts on V2. And thus alpha circle times phi satisfies the first condition for linearity, because you can kind of break it up across this addition over here. Next, let's check the second condition, so 2. Let's see what happens if we have alpha times phi over here, circle times, and we act on a constant times V. So let's say it's lambda times V. Okay, so first thing we do, let's use a definition of the circle times, which is that you can pull this constant out to the outside, which means you get alpha times phi over lambda times V. Okay, next thing we can do, let's bring this lambda scalar out to the front, because this phi is linear, so we can use this second property of a linear map. So this is going to give us alpha times lambda times phi of V. And that's why, again, everything needs to be over the same field, otherwise you have a problems multiplying elements of potentially different fields. So that's why everything's over the same field F. So from here, what can we do? So first of all, technically there's supposed to be brackets over here, but we know from the associative law of scalar multiplication, we can rearrange these brackets to bracket these two guys together. These are from the same field F, and a field is associative for multiplication, so we can kind of flip these two guys around to be lambda times alpha, this guy times phi of V. This is the times on the field, this is the times on W. And now we can use the associative property. This is going to give us lambda times, this is the times on W, we have alpha times on W again, phi of V, brackets like so, because this is an element in W, so makes sense that this is a times W over here. And well, over here, again, we can recompress everything together, the scalar and this map, and this gives us a lambda times, this is going to give us alpha times, but this is going to be the times on the hom VW over here, phi, and this guy acts on just the V. So as you can see, what we've shown is that we can pull this lambda out to the front and it lands over here. So in particular, since alpha circle times phi satisfies these two properties over here, this is also linear. So in fact, the action of this circle times over here, it does indeed produce an element that does again lie in HomVW, so it closes. Okay, this is very quite nice over here. What's left for us to check is actually that these two operations satisfy the other 8 vector space axioms. I won't go through that in this video because it's pretty tedious. It's pretty easy to do anyways. You can also use the fact that you're always mapping to W over here, and since a W is a vector space, you can inherit the vector space structure of W back into the map over here. But we can clearly see once you map everything to W, then it's nice and associative and commutative and everything like that, which means that maps also behave like that, roughly speaking. So once you go through all those 8 axioms, you've shown that these two operations satisfy those axioms, then what you have in the very end is that HomVW equipped with these two operations, which is circle plus and circle times. This all together in one nice package like so, you can say over the field F over here if you want to. This guy's a vector space, which is quite nice. So this is quite a general type of vector space of linear maps. We'll take a look at more specific ones which have some interesting properties and so on in the future, but this is the vector space I wanted to derive in this video. So just some final remarks over here. In the future, I might use this notation where instead of saying a set of all linear maps, set of all phi such that phi is linear, if you've watched Friedrich Scalar's videos, he uses this nice notation where he put a swiggle up over here to denote that this map is linear instead of having to spell it out explicitly over here. But yeah, this is a notation I might use along the way as well if I'm a bit lazy to write this out. But yeah, just something that's worth mentioning as well. So that's all for this video. I hope you guys enjoyed it, and I'll see everyone in the next one.